So,
Thank
perfect. So you've seen some talks being very practical about fundamental weighing and practical applications. Now, I will turn around the topic a little bit to a more abstract area, the digital transformation, which is, I would say, an addition to the abilities we have with new measurement principles based on the redefinition of SI. The second big topic for the international development of the SI, the whole digitization and transforming what we have defined as SI into a digital era. So my talk will focus on this topic, and I will try to show you what actually could we understand under this topic, digital SI. And you may be surprised, bigger than you may have thought. So let's look a little bit at the background. When we speak about digitization, of course, we speak about digital data that we exchange, and we speak about future challenges for this data exchange. So while we have today in the laboratory balance, for example, making single measurements for calibration and so on, that's evaluated with the laboratory software, we'll see in the future emerging areas like the city of the future, modern smart factories, energy grids, and so on, that will all also exchange a lot of measurement data, sensor data from all kinds of areas. So we speak of thousands of sensors that will be installed in the field that will need to be able to communicate data based on metrological principles. And typically, we know that data will be trustworthy if it's traceable to the International System of Units, DSI. However, when we look at our current state of the art, how we report measurement data, then we see we have many individual approaches implemented, which are good for the humans and which have worked for decades for us. But we have to ask, will these standards be usable in the future in this digital world where no more humans, but more and more machines and software aim to automatically act on this data? And the data you see here, it's an example extract from a PDB mass calibration certificate. And you see how many different ways we have in the human way how to represent units. So sometimes units are defined for a list of data. Sometimes units are added to the data entries itself. You have different ways also of stating measurement uncertainty. So it's very clear in the future, machines need you to understand common ways how to deal with such information. Digitalization is not new. That's going on since many, many decades. And today, when we look at the landscape of existing digital standards for data representation, for data exchange in measurement, in industry, in medicine, then we see we have a Babylonic confusion of different solutions. Some are listed here. And the challenge we have with the digital transformation in metrology is to find ways how to bridge gaps between the systems, how to find ways how data from different sources becomes interoperable for us to make it easier to use it. And the message is here, we have the international standards that are the basis for our analog interoperability of measurement data, namely the International System of Units, so the definition of units, guides that describe how to express measurement uncertainties, guides like the international vocabulary and metrology, rolling out basic common terminology and agreed definitions, and also databases like fundamental constants provided by CODATA that are important here. So we see that in the future digital area, we need an anchor of trust to make measurement data really understandable to everybody, to ensure that the accuracy of the data is uniquely addressed and clear to everybody. And so the mission here is to establish and develop the International System of Units as an anchor of trust. And in practice, this means we will have to interoperate and connect different existing systems. And when it comes to the digital SI, it's my perspective, we have not only one system, many systems working closely together, and this is expressed here. So at the top, you may have a gear which is coming from the BIPM, CIPM, which are digitally usable core definitions of DSI core services. Today, this is called DSI Digital Framework. I will present a little bit about this development here. Then we have practical implementations of DSI in data formats, data exchange formats, for industrial applications, for scientific applications. Here I will present to you so-called DSI metadata model. That's a standard that's used, for example, nowadays in many developments for digital certificates of calibrations. And this brings me to the third gear. Having this general standards, we then have a connection of these standards to practical applications, to software products, to data products and metrology, such as digital certificates of calibration, to data relevant for conformity assessment. We speak about smart machine readable standards, research data, future cities as the introduction example, and so on. That will then use this SI-based tools and services to establish better usable data. To understand what the CIPM, the BIPM, and the DSI are doing, I'd like to show you three terms that are defined by Gartner. What does digital transformation mean? And so we have different stages. When we digitize things, we speak about converting paper into electronic formats like image files, PDF files. Of course, this is only the beginning to reduce paper. Then we have digitization. Here we speak about changing our processes from analog processes where you send around paper and fill in paper forms to something that's digital. So you're running the process on your computer, for example. And let's say the big future goal is to have the really ongoing digitization where you use more digital technologies, cloud services, software, and so on, to even change your business models to make processes much more efficient, automated, and to even create new revenue. So you may have heard the slogan to say the data is the oil of the 21st century. And here exactly the CIPM vision for the SI digital framework and the SmartCom vision for the DSI metadata model are starting to make the step from the digitization towards a wider digitalization. Another example of a view on maturity of data is provided from the area of smart machine readable standards. So here you see a classification scheme of data maturity coming from a white paper on smart standards from Lean UKA project IDIS. And it shows you that today we start with maturity levels 1. You have no more the paper, but you have the digital document. That's already saving you some money. Like PDF files. Then level 2 is make these documents machine readable. So when we introduce data formats such as data in extensive markup language XML or JavaScript object notation JSON, we have a format where we can implement software that's able to read this data in a machine. But that's only the beginning. So it outlines that machines are not only required to read this data, but execute based on the content. So we need semantics in data. And the higher levels we reach, like level 4 of machine interpretable content, the better semantics we use and need, the better interconnection of knowledge and metadata we need. And here, really, these formats are trying to make a change in current practice of how we exchange data. Up to the highest level that even machines could change standards and adapt to situations based on these formats. Now, I said I come to the CIPM. So the CIPM has outlined a big vision for the SI digital framework. They say The framework will be in the future a network of different tools, services, and applications that instantiate the digital SI, ensuring that measurements are following fair data principles, that measurement data is machine readable and even machine actionable, for example, in the sense of the smart maturity, and that they support a wider digital metrological traceability in data. This means on the level of the CIPM, DIPM, to work on a digital transformation, digitization of core products like the SI brochure, the international vocabulary, and the guide to the expression of measurement uncertainty. Also look at how will the services in future look like for key comparison data, for calibration measurement capabilities, for mise en pratique with core reference data, time services, and so on. By FAIR principles, this means that the development of services of tools will focus to make the services and data findable to humans and machines, to make it accessible through the web as well, to implement mechanisms to make the data interoperable for humans and machines, and also to establish clear rules for making the data reusable. Finally, also it has in mind to allow these levels of machine actionability, machine interpretability. So this mission is also supported by a CGPM resolution that was agreed on 2022. So in detail, the mission is to foster a globally accepted digital representation of the SI, to facilitate the use of digital certificates in existing infrastructures, to adopt more FAIR principles and metrological data, but also to work with other communities and liaisons to increase the importance of the metrological traceability and by this the trust and measurement data. This work is going on since 2019 here at TASC, an expert group started to develop the first recommendations for the CIPM, DIPM. It was accompanied by a big international workshop on the SI and fair digital data. And what was leading to this resolution I mentioned before, where 6 states, members of the MITRE Convention, have agreed to this vision. And also at the same time, liaisons with international organizations were established. So now we even have a joint statement of intent to cooperate on the digital SI framework with 10 organizations. And very important is also that now in 2024, this task and expert group structure has been replaced by a wider CC-like structure. It's called a cross-sectoral forum for metrology and digitization. Here the work is continued. And also the BIPM has published first digital tool to access the SI data, which is called the SI reference point. So I will explain a little bit more about these 2 last points soon. Just to let you know, the joint statement was really signed by important international organizations. So we have ISO, IEC, CIE from standardization. We have scientific organizations, IC and CODATA on board, but also accreditation is represented, legal metrology, and metrology and laboratory communities such as IMICO and NCSLI. And it's a really important statement because the undersigned presidents and leaders of the organizations really agreed to jointly undertake support for the SI digital framework in the way appropriate for each organization. Really bring forward the digital transformation of the international scientific and quality infrastructure. Now I'd like to speak a little bit about the forum. So the forum has many more goals than just the digital SI. But of course, it's in the focus, so it will advise the CIPM and BIPM on the SI digital framework development and the wider implications on the global digital transformation in metrology and the digital quality infrastructure. It will provide input from metrology to increase confidence, trust in emerging areas. There's something called systems metrology for sensor networks. We speak about trusted artificial intelligence. reproducibility of research results, and so on. Then, of course, to continue the creation of these central digital references for SI information, for definitions and relevant data, and to foster and continue to digitally transform services and products that are offered by the BFM. Then to look at the implications of the digital transformation on operation of the mutual recognition arrangement, which is essential for our traceability campaigns today. And finally, also to work to harmonize international processes of digitizations between metrology organizations, consultative committees, regional metrology organizations, the BIPM, of course, and also create synergies out of these strategies we have at many organizations, and to find opportunities for collaborations with the international organizations. And the forum has been established this year, and it's chaired by PTV's President Cornelia Dens, with co-chairs from Canada, NRC, Jared McDonald, and from Argentina, Inti Hector Lights. And it now has 6 task groups dealing with topics such as AI, data quality, fair principles, calibration and reference materials, certificates. Big topic is metrological semantics, and also the further development of the SI digital framework. And it also has working groups coordinate with the consultative committees, to coordinate with the RMOs on these topics, and to foster and develop a further longer-term strategy. And as the first outcome, I mentioned it, BIPM has published this year the website siddigitalframework.org, and as a first service, the so-called SI reference point. It's really good to look at that, to try out that tool. So it's a database providing you persistent identifiers for the SI units in the dynamic system, and through a web interface as a human, but also through a machine interface API, you can access the data and the definitions of the SI. The whole information, what is the SI, how are the units defined, is also provided as ontology that we downloaded to receive more metadata. And this tool is really good maintained under the auspice of the BIPM. And the core to connect international definitions of DSI to your data. Now I come to the second topic, the implementation of exchange formats based on DSI. So I said it before, we need simple formats for machines to exchange data clearly. And here the SmartCom vision is that we have in the future. I hope you can still hear me.
Yes, is any good?
Okay, yeah, okay, I got my headphone connected again, sorry. So we have the situation that 2 clients need to speak with each other, and typically due to the diversity of formats today, it's very difficult. And normally even humans have problems to understand each other. So DSI metadata model is trying to fill this gap by providing a common reference model that's universal for all measurements, unambiguous, safe, and in the end still easy to use. So the principle of that model is, on the one hand, we have a conceptual definition of what data needs to be exchanged, the language, and we call this metadata model. Then there are implementations, like you have reference schemes for how to write this data in XML and JSON, or even in ontology. And finally, the last bit are assets, so data extracts, like using these implementations to define and exchange data. Like here you see the example of an XML data asset. Now the design is based on different aspects. So certainly in the core is data exchange. So this should be really easy to use machine-readable presentation of the metrology data. Then there's the aspect of interpretation. So it's designed in a way that the data could be used easily and clearly by machines to process data, for example, to perform calculations with the data. Regarding the respect of interoperation, the design is made in a way that there are, in best case, no gaps when it comes to conversion between data in different formats. And finally, in gray, but a topic for the future, that even automatic application of GUM methods is possible based on these data models. So similar to the CIPM, the DSI development has started, let's say, 1.5 years earlier in the SmartCom European project. The project defined a long-term stable version in 2021. And from there on, you can say we're using this format in calibration applications in other areas. We're also collecting feedback from the CIPM work on improvements. So last year, we have made a bigger update of that, including knowledge gained from users from the CIPM, BIPM. This year, we had a guest scientist at PTB developing an interoperability service of the DSI with DSI reference point. And by next year, we want to conclude the development by a last final extension to the core model with some additional uncertainty models. And then the maintenance of the implementations will continue. So the core of the DSI is that we have classical measurement data value with, in the best case, an SI unit. It's the minimum required content. And additional information is providing you a measurement time and, of course, information on the measurement uncertainty. And the implementation is looking on what are standards we can use to implement this data that's suitable for machines. So we have the metrology standards that are implemented here and where the model is based on, but we also have standards from the information and communication technology that are used. And what this means, I show you on the next slide. So here's an example of the data model. It comprises different elements. Some of them are mandatory, others are optional. And for each element, there's a clear definition how the digital data type should be that you need to type in and that the machine could understand. So we have, for example, a label where you can say what's the kind of measurement, and the RFC standard is telling you how to encode the text string you put in there in a binary format. We have a quantity kind following ontology called QDT. Values are implemented according to double precision formats from computer science. The units are based on the SI, and we have other information like significant digits and date time that are also following recommendations from international standards for this data. Up until the point that you even need to say in which binary format do you need to implement XML and JSON. In this case, it's also UTF-8 encoded. And of course, it's containing measurement uncertainties as well, this element. So here for real scalar quantities, the model is providing standard measurement uncertainty values, expanded measurement uncertainty values, and so-called coverage intervals. I don't go into too much detail here, but just want to show you a full example of this data model in XML. So the core is saying you have a SI real element, so this is a real scalar quantity value that have a label like a diameter of something. I see this is a mistake. This should be a mass of a kilogram weight. So the quantity type is mass, and then you have the value. The unit expression that's interoperable with the BIPM in future. Information on a significant digit. Date time when the measurement was made. And then you have a more comprehensive uncertainty statement. So you see it's a univariate measurement uncertainty. It's an expanded measurement uncertainty with a value 0.01. Information on the coverage factor, coverage probability, and also information on the statistical distribution of the data. Yeah, with this, I come to the end of my presentation. So I was very happy that Diego Coppa visited us at PDB this year as a guest scientist, who helped us to develop a service that's linking DSI units to the SI reference point definitions of the units. So today, when you have a unit kilogram, you can call a URL, a persistent ID of the unit in the DSI. That call is resolved at a server at PDB at a web page at dsi.pdb.de by next year. And this service gives back machine readable extract telling you, is this unit kilogram valid in the DSI data model and in the SI reference point? So is it a valid SI unit? Provides you a persistent ID to identify the data in the BIPM SI reference point system. And it provides you a lot of machine readable metadata that's extracted from the BIPM system on properties of this unit. You even have an ontology knowledge graph ready, turtle expression. That's a really big step because this is showing the value of this I reference point to create this metadata, to provide this metadata for our units for future machine actionable data usage. Yeah. Further information could be found in our DSI guidelines and, of course, on the DSI, the framework web page of the BIPM. And with this, I like to thank you and hope I left you with the right impression that the digital SI is a combination of various data services and tools from the BIPM, from the NMIs, from international organizations and future that will all be connected and layering on a common SI core coming from the BIPM CIPM. Thank you.